Hello, welcome to lecture 38. 38. We were in the middle of talking about the examples of Bayesian Nash equilibrium, which is incomplete information game. And if you remember, at the end of the last lecture, lecture 37, I have talked about the roommate game, where there are two roommates, Tim and Sam, and if they do not clean the room, they get 0 and 0. But if they clean the room, not they actually, if one of them, both of them or one of them same, their utility increased by 10. However, the person who cleaned the room, here if Sam cleans, CS would be deducted from 10 because Sam would pay the cost of cleaning. Team also, C team, C T, something like that. So for example, team does not clean it, Sam clean it. Both will enjoy the clean room, which gives the utility 10 to both of them, but only Sam pays the cost because he's the only guy who cleaned the room. If both cleaned it, then both has cost, but then a little bit unrealistic because if both cleaned it, maybe a little bit cleaner. But in this example, it's gonna be 10 and 10. Likewise, if team cleans, only team has the occurring cost and Sam does not. Okay, this is your case. Why this is incomplete information game? The cost of cleaning the room are different for both Sam and Tim. We can have like a high cost and low cost. Sam with probability 1/3, the CS can be 15. In that case, as we can easily guess, Sam will never clean the room. 10 minus 15 is smaller than 0. So now he do not think 0 is guaranteed if he cleans when Sam's cleaning cost is high cleaning cost type Sam, 15, that's gonna be -5, whatever happens after that. So Sam is not gonna clean it when it's high cost. Likewise, Tim is never gonna clean it. That high cost 15 occurs when both Sam and Tim, when he is with probability 1/3. With probability 2/3, Sam and Tim are low cost guys. So in that case, CSCT can be 5. Okay? In that case, even though the other person does not clean it, Tim and Sam would clean it. However, we can see that this both people cleaning cannot be Nash equilibrium. Why? Even though CT and CS are 5, 10 minus 5, 10 minus 5, that would be 5 and 5. But then, team has incentive not cleaning it because 10 is bigger than 5. So, they will deviate. So, clean, when Sam and team are the low-cost guy, cannot be an equilibrium. So, what can be an equilibrium? As I told you, even though it's the same team, the high cost, low cost, high cost 15, low cost 5, different types should be treated as a different player. Same for Sam. So even though we have only 2-player Tim and Sam, because Tim and Sam both can have 2 types, we have to write down as if there are 4 players. And how do you find it? The Nash, not very kind person, didn't tell us how to find it. He just told us how to check it. Once you begin to play Nash equilibrium, nobody has any incentive to change out of it. Okay? So, for some reason, I thought about this. High cost, low cost, they don't clean it. That is easy. I mean, they will never clean it because if they clean it, automatically -5. So they have no incentive to do that. Sam with Tim and Sam high cost will never do that. Tim low cost, he may clean it, but he doesn't. Sam low cost, clean it. How can this be the Bayesian Nash equilibrium? Once again, high cost type, clean, that doesn't make sense. In this case, if Tim low cost, what is he getting? Okay? When he's low cost, he does not know whether Sam is high cost or low cost. If Sam is high cost with probability 1/3, here 1/3, Tim is not cleaning it, Sam is not going to clean it. So it's going to be here. So Tim, we know that Sam low cost will clean it. So Sam will clean with probability 2/3. Sam wouldn't clean it. That means Sam is high cost with probability 1/3. If Tim don't clean it, then Tim may get 10 with probability 2/3, 0 with probability 1/3. If Tim clean it, whether Sam clean it or not, he's going to get 10 minus 5, 10 minus 5. Understand? From Tim's point of view, he does not know the type of Sam, so he will assume that the probability for Sam to be the low cost type and clean will be 2/3. Sam would be high cost type, wouldn't clean it 1/3. If Tim don't clean it, Sam would clean it with probability 2/3, then Tim will get 10. Sam would not clean it because it's high cost type, then Tim would get 0. On the other hand, if Tim chooses to clean, that would be 10 minus 5, 10 minus 5, regardless what Sam does. Okay? So we are going to compare Tim's payoff 5 when Tim clean it, and Tim's payoff 2/3 multiply 10, 1/3 multiply 0, which is 20/3, approximately 6.6666, something like that. Which is bigger? 6.7 is bigger than 5. That's why Tim is not going to clean it. So this Tim high cost strategy, Sam high cost strategy, Sam low cost strategy that Sam would be clean justify Tim's choice that Tim low cost would not clean, because don't clean is better than clean for Tim, especially when Sam low cost always clean. What else should we check? We should check. So the only thing, we know that high cost will never clean it, Tim or Sam. Tim would not clean it as long as the low cost Sam would clean it. Now, why Sam would clean it? Once again, Sam here is a low cost. Tim, we know, never clean it. Tim will always choose don't. If Sam choose don't, it's going to be 0. If Sam choose clean it, 10 minus 5. 5, 0, which is bigger? 5 is bigger. That's what I wrote down here. If Sam is low cost, and knowing that Tim would never clean whether Tim is high cost or low cost, if Sam cleans it, he will definitely get 5, 10 minus 5. If Sam don't clean it, Sam will get 0 because Tim will never clean it. Okay? That is why we show that don't clean is the Bayesian Nash equilibrium. Once again, different types should be treated as a different person. That's why even though it's a 2-player case, we wrote down as if there are 4 players. Okie dokie. You guessed it. Okay. If that is the Bayesian Nash, we can see another. Don't, clean, don't. I mean, Sam and Tim are symmetrical. So if there is an equilibrium where Sam cleans and Tim does not, for the same reason, we can have equilibrium where Tim does not. Tim cleans and Sam does not. Okay? There are actually one more mixed strategy equilibria here, but no, I'm not gonna do that. Here. So is it easy? Yeah, until now, it's not so complicated, you may think, but it can be ugly. Anyway, a little bit more complicated Bayesian Nash equilibrium. That is a modification of cournot competition. Once again, do you remember cournot competition? Cournot competition is where the duopoly or oligopoly companies compete each other. They are producing the same thing and the same market. And if it's a Bertrand competition, they compete with the price. But in cournot competition, they compete with the quantity. Okay? So we will assume the demand of the market is Q equal 2 minus P. So the quantity demanded would be 2 minus the price. Okay, and the firm 1's marginal cost is constant at marginal cost 1 with no fixed cost. What about firm 2? That is the point. I mean, if the firm 2's marginal cost is MC equal 1, 2, then it's just normal complete information cournot competition. However, we are in the middle of incomplete information games. What's the difference? We are going to assume that firm 2 has two types. The marginal cost of firm 2 can be 5 over 4, higher than marginal cost 1. Or with probability 50%, it can be 3 over 4, which is lower than 1. Okay? The point is, even though the firm 2 knows its own marginal cost, firm 1 does not. Okay? Firm 2 has no reason to tell firm 1. And even though firm 2 tells firm 1 does not have any reason to believe in it, really. So, firm 2 knows its marginal cost, but firm does not know firm 2's marginal cost. Only it knows the probability that with probability 50%, it can be 5 over 4. With probability 50%, it can be 3 over 4. What will be the Bayesian Nash equilibrium of the game? You guessed it. It's going to be a calculation. Okay. Voila. If you just understand the first part, it's not that complicated. The profit of first company, the profit of second company when its cost is high, which means the cost is 5 over 4. The profit of the second company when its cost is low, which means the marginal cost is 3 over 4. Like here, 3 over 4, 5 over 4, and the first company has nothing but one type, the marginal cost 1. Okay? So low cost, 3 over 4, high cost, 5 over 4. And here, we wrote down two equations for the second company, firm 2, because high cost, low cost, they are different types, and different types should be treated as different players. Okay? So 2 minus Q1 minus Q2, that is the price of the market. Minus, the marginal cost, that is the profit per unit sold in the market. That is why this is the profit of the second company when the cost is high. The second part, likewise, this is market price minus 3 over 4, that is marginal cost. This is the profit, net profit per sales, multiply the sales of the low cost second company. The first company's profit function is a little bit complicated because the second company's cost can be high with probability of half. It can be low with probability half. So the market Q2 minus Q1 minus Q2H, which is market price, minus 1, that is marginal cost of company 1, that is the net profit per unit sales, multiply sales. This can happen only with probability F. And the low cost case, same with probability F. So because Form 1 does not know the exact type of the second company, it only knows the probability, 50%, 50%. This is profit maximization or maximization of the expected profit. Okay, average profit if you like that way. So the first company can only control Q1, second company with high cost can control Q2H, second company with low cost can control Q2L, so you differentiate them respectively by the variables you can control. Differentiate by Q1, let's forget about half and half in front of it, because when you differentiate, the numbers, constant numbers doesn't matter. So it's going to be 2 minus Q1, because Q1 is multiplied, and Q2H, Q1. Q2 is square, that's why we have this. And here, it's likewise 2 minus 2Q1 minus Q2L minus 1 equals 0. So you differentiate pi 1 with Q1 and set it 0. That is first sort of condition. Okay, simple stuff. Now if you just think it like 5 seconds, you would understand. The pi to h should be differentiated by pi q to h, then 2 minus q1 minus 2q to h minus 5 over 4. q2 pi to l, differentiate by q to l, 2 q1, 2 q to l, because q to l is square, and 3 over 4. And they should be 0 too. Now, this is a headache. From this equation, you have to calculate the Q1, Q2, Q3, Q1, Q2H, Q2L. Well, I spent some time, several minutes to calculate it, and you are supposed to spend several minutes to calculate it. So, okay, I'm going to give you 1 minute. And if my calculation is correct, it's Q1 is 1 over 3, Q2H is 5 over 24, Q2L is 11 over 24. Okay, you have 1 minute, 2 minutes, take your time and calculate. I think it's going to take a good 3-5 minutes, so maybe you can stop this lecture recording and calculate it and see whether the number Q1, Q2H, Q2L you calculated is the same as what I did. Okay, so once again, I remind you, we treat it like there are 3 players and their strategies. The first company's strategy is Q1 in cournot equilibrium competition. The second company is Q2, but we have the high cost type second company, low cost type second company. So high cost type second company's strategy is Q2H. The low cost type second company's strategy Q2L. So you have to calculate all these 3 numbers. If you are still curious, you can have the first company can have high type, low type. It's not only the second company has 5 over 4, 3 over 4. The first company with probably half and half can be 5 over 4, 3 over 4. Then we have pi 1H, pi 2, pi 1H, pi 1L, and we have 4 equations with probability half here, so much more complicated. But then in the past that was in the exam, so you may try it by yourself. Okay, in that case you have to calculate 4 numbers: Q1H, Q1L, Q2H, Q2L. Okay, enjoy your mathematics. Now we are going to move on the climax, another equilibrium concept with other than the perfect Bayesian equilibrium, namely the other than Bayesian Nash equilibrium, namely perfect Bayesian equilibrium. Okay, let's explain it with one example. Okay, there can be many examples, but the most commonly used in my class example is USA and North Korea. This can be like South Korea, North Korea thing. But what is characteristic of this game is this game plays over a period. I mean, I wonder if you have noticed, my example was cournot competition where everybody, the first company, second company, choose Q1, Q2 simultaneously. This cleaning the room kind of thing, Tim and Sam choose simultaneously whether they will clean or not. I mean, if it's not the simultaneous, Tim would wait until Sam cleans. Then if Sam cleans, something like that. But it's not going to be over time. One day, you go there, clean or not clean kind of thing. That's roommate game. The marriage game also male and female decide simultaneously whether marry, single or male, date or no date kind of thing. Okay. But here, it plays over time. We have a name for this. If something happens simultaneous and ends immediately, we call that one-shot game, if you remember. But if the game is played over time, we have a name for that. That is a dynamic game. So we are dealing with dynamic game. If you remember, I mostly explained Nash equilibrium with one-shot game, simultaneous game. However, the point I introduced dynamic game in complete information game, okay, not here, like long time ago, 2 months ago, was at the point where I introduced you the backward induction and subgame perfect equilibrium. So, this empty thread and backward induction is possible if you remember the meaning of backward induction, like even though time flows from right now to the future, backward induction means you should think about future first, then right now. But then that already means it's a dynamic game where at least it has right now, current period, and future period. Okay, so the subgame perfect equilibrium where we have to use backward induction, the game should play over time. So subgame perfect equilibrium cannot exist if there is no dynamic game. So dynamic games are the games that the subgame perfect equilibrium is designed for. And we know why Nash equilibrium was not enough. Subgame perfect is necessary because something like empty thread, stupid Nash equilibrium can survive if we do not apply backward induction. So, for the same reason, in an incomplete information game, if it is dynamic game, we have to have something similar to the subgame perfect equilibrium, and the name is perfect Bayesian equilibrium. Nash equilibrium, Bayesian Nash equilibrium, subgame perfect equilibrium, perfect Bayesian equilibrium. Okay, the economists are not very imaginative and creative people, so the same old names. So okay, I'm gonna explain the real situation later, but what is the point of this? this can be this perfect Bayesian equilibrium situation, the dynamic game in incomplete information game is more complicated than dynamic game in complete information game, because in complete information game, players know each other. But here, players do not know the other person. For example, you're dating a man. The man can be a nice person, not nice person. Of course, you want to get married to a nice man, not these bad boys. But is it easy to tell the bad boys from the nice boys? Not really. And part of main important reason is the bad boys pretend to be the nice boys during the date period. After marriage, wow, they do not hide it anymore. They become bad again. So from female point of view who are dating a man, thinking about marriage, figuring out whether this man is the nice person or not is important but difficult, because the other person pretend to be something else. Okay? That's the main headache of this dynamic game in incomplete information game. Okay? Interested? Yep, we are going to do that in the next, begin to do that in the next lecture. That's going to take about a week. Okay, so it's going to be a long process. See you soon. This has been the lecture 38.